Okay. Thank you, and really sorry for this interruption. Good afternoon, everyone. My name is Sonia Ghosh, and I'm a PhD student at Kaptan Astronomical Institute, affiliated with University of Groningen. Before I begin, I would like to thank the organizers for giving me the opportunity to present my work here. And in case, if at some point of time, if you find the first few slides of my talk sound like the introductory cosmology lecture, please bear with me. Christian have already given a great overview of the different exciting science cases that is possible from the lunar far side and in the very low frequency regime. And in my talk, what I will be going to do is to delve a bit deeper into one of the science cases, namely the 21 centimeter cosmology, and discuss about the impact of the lunar topography on the 21 centimeter cosmological power spectrum. Now, I will give a very quick overview of the evolution of the universe here. So let us just assume that the clock started ticking at the beginning of the Big Bang event, and I hope you have already heard this term. And what we know is that right after the Big Bang, there was a very rapid period of expansion termed the inflation, but we do not quite well understand that. But what we do know is that within the first few minutes of the existence of the universe, the matter and the radiation that we understand today coexisted together as a hot, dense, primordial plasma, soup of plasma. And what happened then is that because of this highly dense state of the matter, the photons were not able to go out, and then the electrons and protons were not able to interact with each other. And so gradually, when the universe started expanding, it started to cool. Now, this cooling led to the decoupling of the photons from the matter, and then the photons started to be freely moving around, and that constitute the what we know today as the cosmic microwave background radiation. Yeah, and okay, give me a few minutes. Sorry, the slides are yeah, it's yeah, it's a little bit, yeah. Okay. Oh, I can go ahead from here. Okay, so now once we have the cosmic microwave background radiation, then it was followed by a period termed as dark ages. And going by the name, this period did not have any sources of radiation and or luminous sources, and we do not have much information about this period. Now, but eventually, like due to the gravitational instability, the is it moving? Yeah. Eventually, due to the gravitational instability, we have the overdense region of the universe started collapsing and started forming the first structures. And that's how the emergence of first stars happened. And this marked the era of the cosmic dawn when we had the first stars. Now, the UV photons from the stars started to ionize the universe. And then, over a period of millions of years after the Big Bang, the universe got ionized again. And this period is termed as the epoch of reionization. I'm extremely sorry. The slides are really creating trouble. Okay, so this is the entire picture of the evolution of the universe. Yeah, and since then, the universe has been in the state of ionization till date. Now, as I already mentioned that we do not have much information about the dark ages because we do not have any luminous sources or stars during that period. And but the underlying physics of the universe during that period was pretty simple. And that is where the Dark Ages Explorer comes into the picture, and it's going to shed light on this period. So, The science case for the DEX is the 21 centimeter cosmology. Now, what is 21 centimeter is the spectral line of the hydrogen atom. And we know that hydrogen atom is a very simple atom with an electron and proton. And the how the spectral line arises is due to the very, very low energy hyperfine spin flip transition in the ground state of the neutral hydrogen atom. Now, during this transition, a photon gets released, which has a wavelength of 21 centimeter or an equivalent frequency of 1420 megahertz. And by the time it gets traveled to us, by the time it reaches to us after spending time after spending so much time in the universe, it gets highly redshifted due to the cosmological expansion. And by the time it reaches us, we are able to detect it in the very low frequency radio frequency regime. So what we essentially measure is the redshifted 21 centimeters signal, which is quantified by the contrast of the spin temperature of the hydrogen atom and the background microwave radiation. And since, as I told you, the signal has been traveling for such a long time, it's very weak in terms of strength. And so we rely on the statistics of it to detect it. And I will be focusing on just the one of the statistics, that's the power spectrum, which you can see in the top row. This is basically the amplitude of the fluctuation of the signal on different spatial scales. Now, just to give you an understanding of what is exactly a power spectrum. So basically, there are three different ways by which we can estimate power spectrum, but for my talk, I will be going to focus only on one of them, and this is the cylindrically averaged or 2D power spectrum. For this, we need to define two spaces, that is image space and the Fourier space. Now, in the image space, we have two antennas, as you can see, and the distance between the two antennas is called the baseline. Then we have to define two directions, namely the direction along the line of sight and the direction that is perpendicular to the line of sight, which essentially gives us the plane of the sky. Now, another way to think about this is in the Fourier space, where you can imagine the k perpendicular to be giving effectively the baseline length. And what we measure along the k parallel direction is basically the line of sight fluctuations, and which basically gives us the time delay. Now, we do not have the 21 centimeter signal alone in the sky, right? We have all other emissions that are happening in the universe. And these are basically the synchrotron radio emission and free emission from the nearby galaxies or the extragalactic sources. And what we have seen till date is the magnitude of this emissions can be 5 orders of magnitude brighter than the signal of interest. So you can well imagine it's like finding a needle in the haystack. So instead, what we use is that the spectral feature of the two different signals. So the signal of interest, that is a 21 centimeter signal, is not smooth along the frequency axis, or is rich in its spectral feature. But the foregrounds or the undesirable radio emissions other than the 21 centimeter signal is very smooth along the frequency axis. So in the Fourier space or this 2D power spectrum space, these two signals occupy different regions in the parameter space. You will see it how. Okay, so we have the along x-axis the Fourier transform of angular scale, along y-axis we have the Fourier transform of frequency. As I mentioned, that the undesirable emission or the foregrounds have a very smooth spectral structure, and so they are expected to be confined to the low modes of the K parallel. Okay, but again, the a radio interferometer is highly chromatic instrument. Yeah, and that induces its own spectral feature in the foreground, and so we get to see that the power of the foreground gets leaked outside the modes where it is not supposed to be present. So this is essentially the picture, how it looks like in the 2D power spectrum. And because of this interferometric response, we see this foreground wedge. And outside this wedge, we get to see the EOR window. Now, this is the window which we actually want to be clean and free of the foregrounds or the undesirable emission, because that's exactly where our signal of interest is concentrated. Okay. a little bit about the Dark Ages Explorer current strategy. So we are planning to have a distributed radio array with 32 by 32 elements, having dual polarized dipole of 5-meter length. And it's going to be a drift scan instrument. It's simply going to look up the transiting sky. And we are planning to have it on the far side of the moon, as uh, Christian said. Uh, okay, so one of the reason why we want to have it on a regular grid is we want to perform a spatial 2D Fourier transform instead of the traditional cross correlation of the antenna voltages that is usually done in radio interferometry, because we have to remember that in for such lunar or space missions, the power and data rates are parameters to think about. So in order to compress the data rates and save power, we are planning to have a regular grid. This brings to my next slide. So I want to particularly highlight this very recent paper where it basically the author characterizes 8 different potential sites for radio array. And what you can see here on the top row is the digital elevation maps, and on the bottom row is the roughness maps at different scales. So the takeaway from this slide is basically that area of slight roughness is very patchy, and it's very hard to get. And that's the motivation of my work. So, okay. Yeah, in an ideal scenario, our antennas are going to be on a regular grid and we will have the correct amplitude and phase of the visibilities. But as we learned throughout the week that lunar topology is really not that smooth, and so the deployment of the antennas might be flawed, and that will lead to incorrect data. And that's where my work comes into the picture. I'm trying to develop an end-to-end simulation where I can understand the impact of this antenna displacement errors on the science case. And this is the schematic of the first order framework of my forward simulation pipeline, where basically, if you look from the right, top right, we have the inputs as the model sky. After that, we have the array layout as our input, which can be regular or irregular. And by irregular, I mean the perturbed antenna positions. And then we simulate mock interferometric observation that gives us visibility, which is basically the fundamental data product for a radio interferometer. Then we see an observed sky. But you can see it's not same as the input sky, and that's really because of the interferometer response. And then finally, we have the 2D power spectrum that help us to understand if there are any errors. Okay, straight to the results. So what you see here is when I introduce perturbation in the antenna position just along the XY direction, what happens. So what you see on your right is the 2D power spectrum with respect to a regular array where all the antennas are perfectly on their place and on the same plane. And on the left, you see the impact on the 2D power spectrum when the antennas have been perturbed to some level. And you can see, if you look at the bottom row of the plot, the red color gets brightened up as we increase the perturbation error. Uh, and this is, okay, just a few minutes. This is the perturbation along Z direction. So in order to model that, I use the stereo observation of the Mare Ingeni, where I use the narrow angle camera data from LRO that has a resolution of around 2 meter actually. And yeah, why Mare Ingeni? Because it's located on the far side of the moon and it has the preferable mid-latitude position that's important for a radio interferometer. And also, this is one of the sites that has been suggested in that paper to be a potential site for radio array. So what I basically do is I take a 600 meter square area from the data, and then I divide it into subsurfaces, into 3 subsurfaces for detailed investigation. So on the top row, what you see is the detrended topographic profile of the surfaces, and on the left is the Hurst exponent, or a way to quantify the roughness of the surface. And on the bottom, again, you see the 2D power spectrum of the regular array and when the array is placed on the different surfaces. Again, if I change my slides, you will see that due to the different topography, the power spectrum changes. and we have power getting leaked to the EOR window. Now, to my last slide. So to summarize that, so we can see that imperfect deployment of the dipole antennas can lead to, can introduce errors. And so it's important that we understand it and try to model for, calibrate for the error. And for that, we need to have an end-to-end simulation pipeline. And as for the future work, I want to make it more realistic. So we plan to have the 21 centimeter signal model itself and various other complexities. Uh, Thank you. And yeah, sorry for the interruption because of the slides.